To introduce our today's speaker is Professor Gerard Helminck from the Continental Differential Institute in Amsterdam, and this is a joint talk with Gerard's brother Luke. And well, if you will go to the first page, it would be perfect.
Okay. I move. Okay.
No, it's still page 7.
And which page you want?
I think the first one.
That is this one.
Okay, so you begin with, okay. So, Gerard, you are welcome.
Okay, thank you for the invitation, Joseph. It will be a pleasure. I will discuss, as you can see in the title, an integrable deformation of a commutative algebra. And since we know from the work of Adler van Moerbeke that in general integrable hierarchies start with some Lie algebra, where you split the Lie algebra into Lie subalgebras, then you take in one component of the decomposition, you take a commutative Lie subalgebra, and then you deform it with the group of the other component. And for instance, if you take Kp, then you have the pseudo differential operators. Then the decomposition you work with is splitting the pseudo differential operators in this derivation partial into differential operators in partial and strict integral operators. That means only negative powers of partial. Then you take inside the differential operators, you take the C algebra generated by partial, and you conjugate partial with an element of the group belonging to the other component, and that's an element of the form 1 plus lower powers of partial. And then you get a deformed element of the pseudo differential operators, and you look at the equations, Lex equations of this deformed operator L. Now, what I will do here is I don't start in the pseudo differential operators, but in the pseudo difference operators. And I take the decomposition in the pseudo difference operators in the skew Hermitian operators in the pseudo difference operators, and a lower triangular Lie subalgebra. And then I will deform the generators of this commutative subalgebra in the skew Hermitian elements by a pseudo difference operators, pseudo difference operator of the form the identity plus strict lower triangular, and that gives you this commutative Lie algebra is CSH, skew Hermitian, over C. And the corresponding hierarchy is the CSH-C hierarchy. Now, the deformation of this commutative algebra will be by conjugating with an element of the group of the opposite component. And if this generator of this dressing operator of this deformation satisfies a certain set of equations, the Sato-Wilson equations. There's an analog of the equations used in the P hierarchy, and go back to Sato and Wilson, and then you get a solution of this hierarchy. Now, what is a good way to get solutions of the Sato-Wilson equations? That's through the notion of linearization. That then you introduce a left module for the pseudo-difference operators. In the pseudo-difference operators, you can consider a set of equations. And if you have special elements that satisfy these equations, then you get a solution of the CSH-C hierarchy. And those special elements are in this model are called wave matrices. Now, that's all very formal until now. And now we must make everything convergent what we want. And that's done in the last section, the geometric construction of the solutions. So I will start with discussing the pseudo-difference operators. You take an algebra of real functions, RR, and then take its complexification, R. And the alpha tensor F with F in RR and alpha in C is simply denoted by alpha F. Complex conjugation on R is done by...
Here, I'm sorry. At least
yes.
I see page 7 only, and that's all.
Page 7?
Yes,
is... Oh, that's strange.
Well,
I will go back
maybe
one.
It is my problem, but I see only page 7, and nothing changes.
And now I'm in the beginning again, and now I check.
But I see the page 7.
Hey.
Alec, what do you see?
Yes, me too. Page 7.
Yeah, so it's not my problem. It's the general problem.
Oh.
Try again to share the screen.
Okay. I stop sharing and we do it again. Okay.
Yes, and then share again.
Okay, wait a minute. And there it goes. And now.
Probably. So the first line is pseudo difference operators 1, correct?
Yes. Yeah.
Okay. Then proceed, please.
Okay. So I started with discussing the pseudo-difference operators. The coefficients are RR. That's an algebra of real-valued functions. You take the complexification R, and you then leave out the tensor product between an element from C and an element from RR, and you simply write alpha F. And if you want to complex conjugate, then you do that in the alpha term. An element from the real algebra RR is called positive if all its values are. So, and we write F bigger than 0. Now, we take all the matrices to be ZxZ-matrices with coefficients from R. That's only a space. The transpose of a matrix is, as usual, flipping the indices, and the adjoint is adding to flipping the indices complex conjugation. Now, the pseudo-difference operators are built up from two types of matrices. The diagonal matrices, if you have a set numbered by the integers, then you can make a diagonal matrix as indicated on the screen. D1R are the that's the algebra of all diagonal matrices, and you can embed the ring R inside this diagonal matrices by putting everywhere on the diagonal the same element R. Now, the next matrix I need is the shift matrix lambda. It's it has ones on the diagonal just above the central diagonal, and for the rest zeros. And the elements lambda act by conjugation on the diagonal matrices, so they normalize it, and what you get is simply a shift along the diagonal. The diagonal of the ds goes over to the diagonal of ds plus f. And each element in the Z by Z matrices can then be decomposed into the sum of its diagonals. And the highest diagonal of the matrix is simply the diagonal matrix with on the diagonal A as S plus I, and the product with lambda to the power I. Now, inside the Z by Z matrices, we consider the matrices that have only a finite number of positive diagonals. So it is bounded above by some number n. Because of the action of lambda on the diagonal matrices, you see directly that this is an algebra. And recurrently, you prove that an element who starts with a diagonal for which the highest diagonal has invertible diagonal part, then this element is invertible in this algebra. Now, if an example is the element capital delta is lambda minus the identity, that's an invertible element. It is the matrix belonging to a difference operator, And then you show easily that you can write pseudo difference operators also as a sum of over the integers of a diagonal matrix times a power of delta to the power I. And this explains the name difference, pseudo difference operators. For the difference operators are the positive powers of delta I, and what you do is you add arbitrary negative powers of delta, and then take arbitrary diagonal coefficients, so that it's similar to the construction of the pseudo differential operators in partial. Now, in the pseudo difference operators, I take the real subalgebra of skew Hermitian matrices. So that means that A star is minus A. So that means directly that all those elements, because they have a upper bound in the number of positive diagonals, that they are finite band matrices. General elements can be written in the form displayed in the center of the sheet. You have arbitrary elements above the central diagonal. The central diagonal should be purely imaginary, and all the other components are free. Now, what is a complement of this Lie algebra? And now, then you can take the lower triangular matrices, of which the central diagonal is real, and all other the lower diagonals are have arbitrary coefficients in the diagonal matrices. Now, that gives you a direct sum of the pseudo difference operators in two parts. And you can split an arbitrary elements, you can project it onto the first component according to the formula given there. And it's the projection on the other part, on the skew Hermitian part, is given by the formula at the bottom. Now, what is the group corresponding to this lower triangular matrices? And now, the central diagonal is an element with real values. So if you take the exponential, then the image gives on the central diagonal elements e to the power r. So that's an element that will be invertible. So you get that a central diagonal of the exponent will be an invertible element, and because you take the exponent, the r has to be a real valued function, it will be positive. So this group script p minus r we see as a group belonging to the Lie algebra P minus R. And this is the group that we will use to deform the commutative algebra in the skew Hermitian matrices over C. Now, there is a real analog. For you, you can start instead with a commutative real algebra RAS. Then in the real Lie algebra, you consider the antisymmetric matrices. So instead of taking the adjoint, you take the transpose. Those elements can also be described. Here you have no central diagonal, as you can see, that's missing here. And for the rest, you can take the DJA arbitrary. Now, what is the complement of this Lie algebra in the pseudo difference operators over RAS? That's the group P smaller or equal to 0, and it consists of all elements that are in D1 over RAS. And that is a real Lie subalgebra of this. Now, then we have again a decomposition like we had before for the complex case. Then P, if you can compute again the components on the element on the Lie algebra P smaller or equal to 0. That is this formula. And the projection onto the antisymmetric matrices is given by P minus its projection here above. Now, oh, that's wrong. Sorry. Now, what is the group corresponding to the complement of the antisymmetric matrices? That's script P smaller or equal than 0. And then that's lower triangular matrices with on the central diagonal. There are only invertible elements. And in the central diagonal also has to be positive. And that will be the group that we use in the real case to deform the commutative Lie algebras. Now, in the skew Hermitian matrices over C, he takes a real Lie subalgebra spanned by the following elements: G1, J1 is lambda to the power J minus lambda to the power minus J. So that those are the real matrices, but there are also some complex pure imaginary one, that's G02 and GJ2. and we use the index set of this we denote by sigma, and that's what you can say about this Lie algebra spanned by those elements. That is a maximal commutative Lie subalgebra of, so it is optimal as for commutativity, and G sigma sigma in the index set are the basic directions. And we extend. We need. Oh, wait a minute. I pushed. Okay. Yeah. Now, because we are going to deform those basic elements, so script p minus 1 minus r deformation of the G sigma is a collection of matrices script G sigma in the pseudo-difference operators, so that for all elements sigma from the index set, the script G sigma element obtained by conjugating with some G from script P minus R by conjugation, and is G we call the dressing operator of the deformation. Now, since G02 is a multiple of the identity, it remains the same under this deformation. Now, we will need a set of evolution equations that we require of this deformation. So we assume that the real ring RR is equipped with a set of R-linear commutative derivations, the sigma, and this partial sigma will be an algebraic substitute for differentiating with respect to the flow parameter of the flow corresponding to G sigma. That's what you, and this is then the algebraic form of this last statement. Now, we extend the partial sigma to C-linear derivations of R by putting partial sigma alpha F equal to alpha partial sigma F. And by letting this partial sigma act on all the matrix coefficients of the pseudo-difference operators, you get a C-linear derivation of this algebra. And you use the same symbol to describe this C-linear derivation. Now, the evolution equations we require of P minus R deformation are determined by the decomposition we started with of the pseudo-difference operators, and consist of all equations that the partial sigma 1 of G sigma 2 is the projection of G sigma 1 on the skew Hermitian matrices, and the commutator with G sigma 2, and that's equal also to the commutator of G sigma 2 with the projection of G sigma 1 on the other components. This last fact follows directly from the fact that all the G sigma commute. Now, so these equations are the Lex equations of the ZxZ hierarchy. And if you have script P minus R deformation of the basic directions that satisfies all the equations for, you know it a solution. And in the setting R partial sigma, that's the data of R combined with the partial sigma, and that we call a setting. Now, the Lex equations are called the Lex equations of the hierarchy, and there is always a trivial solution, namely if you take all the script G sigma equal to G sigma. For then all the derivatives are 0. Now, you have the same the real analog. You take the algebra CASR spent by the elements Fj, lambda to the power j minus lambda to the power minus j. And script j is the index set. And also this is the maximal commutative Lie algebra of the antisymmetric matrices over R. And the Fj are the basic directions of this real Lie algebra. Now, the elements of CASR will be conjugated with the elements from the group script P smaller or equal than 0. And therefore, we introduce a notion of a script P smaller or equal to 0 deformation of the Fj. That will be elements script Fj, such that Fj is obtained from script Fj is obtained from Fj by conjugating with an element from Z from the group script P small or equal to 0. And G is again the dressing operator. Now, what will be, we need again, oh, wait a minute. We need again that the real ring RAS is equipped with a set of R-linear commuting derivations. And that's again del partial J is an algebraic substitute for differentiating with respect to the flow parameter of the flow corresponding to Fj. And again, partial J, you let act on the coefficients of the pseudo difference operators over RAS, and you get an R-linear derivation of this algebra. And we ask for a script P smaller or equal to 0 deformation, script Fj of the basic directions that say satisfy the following Lex equations, that partial J1 of script Fj2 is the projection of script Fj1 on the antisymmetric matrices commutator with script Fj2. And this second expression you get for free because that follows from the fact that all the FJ, script FJ commute. And again, the algebra together with the set of derivations, partial J, we call a setting. And if you have a script P smaller or equal to 0, a deformation of the basic directions in the antisymmetric matrices, then that satisfies all the equations 5 that you call a solution in that setting. And those equations are again Lex equations, and they also possess a trivial solution. Now, now all the time we have this dressing operator, and now we will derive an equation such that if that is satisfied by this dressing operator, then you know that that dressing with such an element gives you a solution of the hierarchy you are discussing. The both sets of Lex equations of the complex hierarchy and the real hierarchy are compatible systems. For if you look at the projections of the script BS, is the projection on the skew Hermitian matrices of the deformed generators, script G sigma, then they satisfy the zero curvature relations. And this you prove by exploiting the Lex equations and using that the two Lie algebras where they belong to have zero intersection. And the same holds for the projections Cj of the deformed elements script Fj. Cj is the projection on the antisymmetric matrices of these elements, and they also satisfy the zero curvature relations, and the argument is the same. Now, from the fact that the elements B sigma, the script B sigma and script Cj satisfy both zero curvature equations, you can still write down two more elements that satisfy zero curvature relations, namely the script alpha sigma is script B sigma minus Z sigma. And in the real case, the script dj is script cj minus script fj. From the zero curvature relations that we already had for the B sigma and the script cj, you easily proved the zero curvature relations for those elements. Now, this compatibility comes then on the next page. We come to the Sato-Wilson equations for our hierarchies. Suppose you have a script G sigma that is obtained by conjugating its basic directions with an element k. If you the script alpha sigma are defined as above, then there holds that if the dressing operator satisfies the following equation, that partial sigma of k is script A sigma times k, then we have a solution script Z sigma of the ZxZ hierarchy. And because if you bring k to the other side here, you get the partial sigma k times k inverse is a script A sigma. And that equation was called in the KP case the Sato-Wilson equation. So we use the same words here. Now the same holds for the real case. If you have the script Fj obtained by deforming with P, and P satisfies this equation for the dj, then the script Fj are a solution of the. So if you have a way to get those equations, this one and the one on the other side, then you have a way to find solutions of both hierarchies. Now, how can you do that? In the sequel, we will introduce a model for a module for the pseudo difference operators in both cases. And in this model, we will construct special vectors called wave matrices. And if these wave matrices satisfy a set of relations in the module, then that's enough to get the Sato-Wilson equations. And that we will show next. So we start with script P minus R deformation, the script G sigma. The script B sigma are just as before. And also, so we have a script P smaller or equals on 0 deformations, script Fj of the basic directions. Now, we first give the manipulations to get why that leads to solutions of the two hierarchies. But like if you see the manipulation, then it's clear that this set of equations are linked to the hierarchy we are discussing. For in the complex case, you take the script G sigma. One searches in the module for an element phi that satisfies that if you multiply phi from the left with script G sigma, it's equal to phi times G sigma. And the most important one is if you apply script partial sigma on phi, then it should be equal to the action of the projection on the skew Hermitian matrices of the script G sigma times phi. This set is called the linearization. For I don't say yet what the phi is but we will see what how you get the Lex equations. You apply to the first equation, you apply partial sigma 1 and to the first equation for sigma 2, and you use a Leibniz rule. So the Leibniz rule you see here. Oh, wait a minute. It's here. And this element, it does not depend on the parameters, so you only get the derivative of here. Then you substitute the second one for the partial sigma 1 and script G sigma 2. And if you pick up all the pieces, then you get the Lex equations times phi is 0. Now, if the element phi is such that that the annihilator in the pseudo difference module is equal to 0, then automatically the script G sigma satisfy the Lex equations of the. So we must make sense of those equations above and take care that the annihilator of phi is equal to 0. Now, in the real case, you have the similar equations. Now the script Fj psi is equal to psi times Fj. And the action of partial j on psi is a projection on the antisymmetric matrices of the deformed basic generator times psi. And the similar manipulations gives you then the Lex equations for the Fj if the annihilator of psi is also 0. Now, what will be I will first give the structure of the model for the complex case. Now, what we need from the manipulations that you can multiply from the left with elements from the pseudo difference operators like like the deformed Gj. Oh, that should be a sigma. The deformed G sigma. And the projections on the self skew Hermitian matrices. From the right, look here for the real case. You should have that you can multiply with elements of the basic directions G sigma, and there should be some action of the partial derivatives partial sigma on phi, and that satisfies Leibniz with respect to the left action of the pseudo difference operators. and you should have no annihilator for phi. Oh, that's the wrong direction. Now you look to the elements. What would psi be in the case that you take the trivial solutions? We had the trivial solutions taking the G sigma. Now then the equations become that phi 0 has to commute with G sigma, and if you differentiate with partial sigma, then it should be simple multiplication with G sigma. Now think of partial sigma as a substitute for differentiation with respect to the flow parameter correspond to G sigma, and that brings you to phi 0 is the exponent of the sum over all T sigma, G sigma, where T sigma is the flow parameter of. Now, if you take good convergence conditions, then this element is a well-defined Z matrix, and it commutes with the elements G sigma. Now, the module for the linearization will then consist of formal perturbations of these trivial solutions by formal multiplying from the left with elements from the pseudo-difference operators. This collection we call OSH. It is the collection of formal products of an element of here on the left of all the arbitrary elements from the pseudo-difference times an exponential factor which is given by corresponds to the trivial solution. Now, even if this is a well-defined Z matrix, then the product of this one and that one, this is a well-defined matrix. If this is, then you need convergence conditions to make sense out of this product as a well-defined Z matrix. And you call those formal products, we call oscillating matrices for the hierarchy. Now, what will be the left action? If you have an element L1 from the pseudo-difference operators, then you simply multiply with it on the perturbation factor. And also, since phi 0 commutes with all the G sigma, then you push in from the right this factor G sigma, like this. Now, if you the action of partial sigma on this formal product is simply applying a partial on this part, and on this part, it is multiplication with G sigma, and you use Leibniz. So, and then you get this action, and you see that this element belongs again to the pseudo-difference operators. Now, this oscillating matrices is a free model with generator V0, and an element phi from the equations 9 and 10 has 0 annihilator as soon as you take the perturbation factor phi hat to be invertible. And the first equation implies then that G sigma is equal to conjugating with phi hat. This brings us to the following definition. An oscillating matrix of the form phi is phi hat times phi 0, with phi hat belonging to the group, the deforming group in our case is called a wave matrix. Wave matrix for the elements script G sigma. If phi and the script G sigma satisfy the equations 9 and 10. In that case, the manipulations are to get the Lex equations are well defined, and you know that Z sigma form a solution. Now, to get the module for the real case, then you look at the solution psi 0 of the linearization corresponding to the trivial solution, simply that script fj is equal to fj. And then you end up that psi 0 is the exponent of the sum of the tj fj, and summation over all j in script j. And here you can make under suitable conditions, you can make a well-defined Z by Z matrix. Now then, the module of oscillating matrices for the CAS-R hierarchy consistent of all formal products of a perturbation factor and from the pseudo difference operators for RS and psi 0. Now, if you replace everywhere phi 0 by psi 0 and the pseudo difference operators over R by that of RAS, then you get right model structure on this model. Also, the right action of the fj, you get in by replacing G sigma by fj and phi 0 by psi 0, and the same with zowel good way the action of the partial j on OAS you get by replacing everywhere a partial sigma by partial j, phi 0 by psi, and G sigma by fj. It is also a free module for the pseudo difference operators, and an element psi is psi hat times psi 0, with psi hat belonging to the forming group in the real case. That's called a wave matrix. If the script fj obtained by conjugating with psi hat satisfies the equations of the linearization for this hierarchy. And then the script fj are a solution. Now, the wave matrices for the complex hierarchy and for the real hierarchy are in their own context the analogs of the Baker-Archier functions for the KP hierarchy. Then you also had the splitting of in functions in Z that have essential singularity in this exponential part, and that have only a pole at infinity in the perturbation part. Now, to get the second equation in there is still the second equation in the linearization. There is still the following result. If you have an oscillating matrix of the right form, if you can show that for all sigma, if you take the derivative with respect to partial sigma, and you can show that it is equal to a skew Hermitian matrix S sigma, then automatically S sigma has the right form, where G sigma, script G sigma is conjugating the basic direction G sigma with phi hat. And then you know, so you only have to prove that this matrix has the right form, and you don't have to prove that it is directly this, that you get out of the machinery. And the same with if you have an element psi in the real model with psi, this should be a psi, should be in the group that takes care of the perturbation of the deformation, then you only have to prove that partial j on psi is equal to an antisymmetric aj times psi, and then automatically this aj is equal to the projection of script fj on the antisymmetric matrices, where script fj is conjugation with psi hat. So then you have automatically, so this we will use at the construction. Now, we are at the last part of the talk. That's giving the analytic construction of the solutions. I take the Hilbert space over K is or the reals or C of Z by 1 matrices with coefficients from K and satisfying this convergence conditions. On HK, we put the standard in the product. That is the sum over all elements in Z of Xn times the complex conjugate of Yn. So the elements En form orthonormal basis of this. And if you have a bounded operator on HK, then so that means a k-linear operator from hk to itself with bounded norm, then the matrix B is taken with respect to the Hilbert basis we described here. And the action of B on X corresponds then in coordinates with the action of multiplying with the matrix B, and that we describe by MB. Now, first we are going to describe the commuting flows that play a role in the complex case and the real case. As we saw in the linearizations, we must make sense of these exponential factors, and that we give them a convergent footing. If you look at multiplying with the element G sigma, then you can easily see that the norm operator norm of G sigma is smaller or equal than 2, and the same holds for the multiplying with the Fj. So we take our parameters. The T sigma is all the coordinates T sigma, and the Tj, that's all the Tj in the following two spaces. T sigma is in L1 sigma, and that consists of all parameters. Oh, sorry. T sigma in R, such that the sum of the absolute value of T sigma and the sum over all sigma in sigma is smaller than infinity. And the same L1 of script J consists of all Tj real parameters, such that the sum of the absolute value of Tj is smaller than infinity. Now, right, and we equip those spaces with the norms 1, a T sigma 1 and Tj1. And now we can define two analytic maps. First, sends T sigma to gamma sigma T sigma. And gamma sigma T sigma is the exponent of the T sigma M multiplication with G sigma. Now, because of the conditions on T sigma, that maps L1 sigma to the bounded operators on HC. And on the same way, we the Tj should be here. Here should be a script J, and here a script a J. A J. This is sends the T script J to the exponent of the sum over all J, Tj mf J. Oh, that is another typo. And maps L1 of J to the bounded operators on the real form of the Hilbert space. And the images of those two maps, we write gamma sigma and gamma script j. Now, next we specify the settings for the complex hierarchy. We choose for the algebra RR, the infinity functions on the space L1 sigma, with values in R. And then R, the complexification consists of all C-valued C infinity functions on L1 sigma. The matrix of gamma sigma T sigma is a well-defined matrix of a bounded operator, and also coefficients of this matrix belong to R. And for the derivation partial sigma, we choose partial derivatives with respect to T sigma. And we proceed in the same way in the real for the real hierarchy. We take for R as the R-valued C infinity functions on L1 of J, and the matrix gamma j tj is a well-defined matrix, and all its coefficients belong to the ring RAS. And for partial j, we choose differentiation with respect to the flow parameter tj. Then next, we are going to describe the group of transformations of each group whose homogeneous patience leads to solutions of the of both hierarchies. So let's S2 of HK be the Hilbert-Schmidt operators in HK. S2 of HK consists of Hilbert-Schmidt, means that the absolute value of all the matrix coefficients squared and then summed over all the indices has to be finite. It's if you take the transpose or the adjoint of such a Hilbert-Schmidt operator, then it stays in the Hilbert-Schmidt operators, and that's clear from the definition. And the Hilbert-Schmidt operators is a Hilbert space with respect to the inner product given by the inner product AB2, and that is the sum over all elements in N of the inner product of En with A star B En. Now, the group G2 of K will be all the elements of the bounded operators on HK that have the form G is the identity plus an element in the Hilbert-Schmidt operator. It is a Hilbert-Lie group because with Lie algebra S2 of HK. And it's the two decompositions that we had on our pseudo-difference operators. They induce also splittings of the two spaces of Hilbert-Schmidt operators in the direct sum of two. In the complex case, you get the collection of skew Hermitian operators in the Hilbert-Smith operators. They are Hilbert-Smith operators such that A star is minus A. And the other one, H2 of HC minus, that is its complement that consists of all Hilbert-Smith operators that are lower diagonal and on the central diagonal they have only real elements, and the other diagonals can be arbitrarily complex. And for the real case, we have the antisymmetric Hilbert-Smith operators. Simply the transpose is minus A, and here the Hilbert-Smith operators smaller or equal to 0. That is the lower triangular matrices with arbitrary diagonals, real diagonals. Everything is real. Now, and to the first two complex, now there corresponds two groups. To the first corresponds the group U2 of all unitary operators in G2 of C, and to the second the group P minus of all the lower triangular matrices that have on the diagonal only real strict positive entries. Now, those groups U2 and P minus have nothing in common. So the map from P minus to U cross U2 to G2C, and the map we call I sub C of P minus U is equal to P minus times U is injective and locally a diffeomorphism. Now, Beltita has shown that this map is also surjective. And the decomposition of G2C determined by the inverse of this bijective map IC is called Iwasawa decomposition of G2C. Now, because that map is a bijection, then if you take I tilde C, that is a small variation of what we had, and now we take P minus inverse times U. That's also a diffeomorphism between P minus cross U2 and the group. And we will use this twisted Iwasawa decomposition, this the inverse of I tilde C at determination of our solutions. For each element G in the G2C, there is a lower triangular matrix in P minus and a UG in U2, such that P G is equal to P minus G inverse times UG. Also, in the real case, you also have two legal subgroups of G2R. The first corresponds to the group of transformations of orthogonal transformations O2 in G2R, and the second is the Lie algebra of the transformations P smaller or equal to 0 in G2, consisting of lower triangular matrices with a strict positive invertible central diagonal. Again, we have that those two groups have nothing in common, and multiplication IR from P smaller or equal to 0 cross O2 to G2R P smaller or equal to 0 times O times is an injective and also locally diffeomorphism. And in the same paper, Beltita proves that it is surjective also in the real case. Then the inverse of IR is the Iwasawa decomposition for the real group. And as in the complex case, then you can also add a small twist here. Then you take I tilde R of P smaller than equal times O is the inverse of P smaller or equal to 0 times O. That's also a diffeomorphism, and we use the inverse of this twisted Iwasawa decomposition determined by the inverse of I tilde R. And that the statement is then that every element of G2R can be split in an element from P smaller than equal to 0 of G from P smaller from the group P smaller than and equal to 0, and an orthogonal element from O2, such that you have this decomposition. Now we are nearly there. Now we take in the complex case, and we proceed in the same way. You take an element, you conjugate the element G from the group G2C with an element from the flow group. That gives you a new element in the same group. And to this element, you apply the twisted Iwasawa decomposition. Then you get gamma sigma T sigma gamma G times gamma sigma T sigma minus 1 is equal to P minus G T sigma minus 1 times UG of T sigma. And both elements depend in a C infinity fashion on T sigma. Now, on the matrix level, this identity yields that capital phi is this element. Is the product of P minus G T sigma, gamma sigma, T sigma. Now, the matrix of gamma sigma T sigma is nothing but phi 0 from the linearization times an element from the group. A lower triangular matrix with real central diagonal, that's positive. So phi is a candidate wave matrix for the hierarchy. And in this case, all products of elements, this is no longer a formal product. This is simply the product of two matrices corresponding to bounded operators. Now, then we know thanks to this proposition 8, that it is sufficient to show that the action of partial sigma on phi is equal to skew Hermitian matrix as sigma. Now, if you compute this one, then you get, if you use one side, then you get this expression. And from this is an element that belongs to the pseudo-difference operators. If you apply partial sigma to the other, to the right-hand side of equation 21, then you get the following expression, this one minus this one times phi. Now, this one, you can replace, because it is a unitary matrix, it is the same as taking the adjoint. And here you have conjugation of a matrix G sigma, skew Hermitian, with a unitary one, but this one is then also skew Hermitian. Now, to show that this one is skew Hermitian, now then you use the identity that UG T sigma times UG T sigma adjoint is the identity, and then you see that this is again a skew Hermitian. So we have that all the sigma, S sigma, are skew Hermitian, and that proves that phi is a wave matrix for the CSHC hierarchy. Now we can apply in the real case. No, first still something else. If we replace G by G times U, with U an element of the unitary group, then we get that you conjugate here this, you put this one gives the vector P minus G T sigma inverse times UG. Now this is a unitary matrix conjugating with gamma sigma the element U gives again an element in U2. So what you see that we may conclude that this element is equal to that element. In other words, G and G times U gives the same solution of the hierarchy. And in the antisymmetric case, you take G2 and R and follow the same approach. Now, then you are at the final results. Then the solutions for both hierarchies can be obtained as follows. For each G in Z2 of C, consider this perturbation of the basic directions, where the P minus G T sigma comes from equation 21. Then this gives you a solution of our hierarchy, and the solution doesn't change if you replace G by an element G times U. Hence, the homogeneous space G2C U2 mod U2 determines the solutions of this hierarchy. And in the real case, you get for each real matrix in the group G2R, and each J in script J, then you look at this perturbation of the basic directions Fj, and these elements are a solution of the CASR hierarchy, and the solution doesn't change if you replace G by G times an orthogonal element from G2R. Hence, this symmetric space determines the solution of the CSHR hierarchy. And that brings me to thank you for your attention.
Thank you, Gerard. Thanks a lot. Questions, remarks? No question. Okay. Gerard, thanks a lot. Regards to Luke. And I hope this is not your last talk at our seminar.
No. When I have something new
Okay,
again.
yeah. Well, we will be in contact. I'll write to you. So we skip the next Wednesday, and quite probably we shall meet on the 1st of May. Thank you for visiting this session, and have a good time. Goodbye.
Okay. Wonderful.
Yeah. Bye-bye.
Bye-bye, Joseph.